Normally, we have heard about the mechanical resonance. So, mechanical resonance generally occurs in certain conditions. So, but now in electrical resonance also, certain conditions are required. So, there means in electrical circuits there are two types of circuits. One is called the series circuit, another is called the parallel circuit. So, the conditions for resonance to occur in the electrical circuits is different for series as well as parallel. So, in case of the whether it is a series circuit or it is a parallel circuit, always three elements, mostly the inductance and capacitance, must be present in the circuit so as to resonance to occur. So, therefore, today we will discuss about the resonance in series RLC circuit. So, this is a series circuit containing resistance, inductance, and capacitance. So here the supply voltage is given, AC supply voltage is given with certain frequency. Now, whenever this is being given, whatever the voltage is being supplied to the circuit, the total voltage will get divided into these three elements. So, the voltage across the R or the resistance we can say that is VR. The voltage across the inductance, that is VL, and the voltage across the capacitance is VC. So now the vector sum of these VR, VL and VC will give the total supply voltage V, because this is an AC. In case of the VC, we can say the algebraic sum of all the voltages will be equal to the supply voltage whenever the elements are in series. But this is an AC case, so therefore the vector sum of this VR, VL and VC will give the supply voltage V. So if you will draw it in a phasor diagram, then it will take the common reference as current I, because the same current is flowing from both R, L and C. So therefore, if we take the reference as current I, then the voltage across the inductance will always be in phase. Voltage across the resistance will always be in phase with the current. Because in a purely resistive circuit, current and voltage always remain in the same phase. So here we can say this is VR. Similarly, in case of purely inductive circuit, current always lags the voltage by 90 degree. So therefore, you can say here the voltage will lead the current by 90 degree. So this is VR. Similarly, and this is 90 degree. Similarly, in case of purely capacitive circuit, the current always leads the voltage by 90 degree. So therefore, you can say the voltage will lag the current by 90 degree. So we can draw the phasor diagram here. This is VC. So here we are getting three components of the voltage. One is VR, another is VL, another is VC. So to find out the vector sum, one will be this y-axis will give you the reactive component and x-axis will give the active component. So if we change the frequency, then what will happen? This VL and VC will change, because we know that VL is equal to I into XL and VC is equal to I into XC. And again, XL is equal to I into omega N and XC is equal to I into I by omega C. So therefore, this XL and XC decides the amount of the magnitude of the voltage across the inductance and capacitance. So if we change the frequency, what will happen? This VN and VC will change, because the XL and XC will change. So when frequency will increase, the XL will increase, because XL is equal to 2 pi XL is directly proportional to F and XC is inversely proportional to F. So therefore, if the frequency will be increased, the XL will increase, and if the frequency will increase, XC will decrease. So during the variation in the frequency, a certain stage will come when the XL will be equals to XC. But if XL will be equals to XC, then VL will be equals to VC. So in that case, what will happen here? When Vn and Vc both will be equal in magnitude, but they are opposite in direction. That means out of phase by 180 degree. So therefore, the net reactive component of this voltage becomes zero, and that is the condition for the resonance to occur in the series circuit. So condition is that net reactance voltage is equal to 0. So during the variation of the frequency, wherever there will be, means the magnitude of XL or XC will be same, or the magnitude of the capacitive reactance as well as the inductive reactance will become equal, then the voltage across the inductance and voltage across the capacitance will be equal, and therefore the net reactance will be equal to 0. So whenever the net reactive voltage becomes 0, the total voltage V will be equal to VR. So that means the voltage across the resistance will be maximum. So that is the condition for resonance. So if you draw the graph, that is the voltage, sorry, XL, XC and R versus the frequency, then the graph becomes, this is your frequency, or you can say that is omega or F. Here it is 0. So then this is R. Now XL is directly proportional to frequency. So therefore we can draw this as XL, and XC is equal to 1 by omega C, and that will be the negative portion. So therefore the graph for XC becomes like this. This is XC. Now if we add all these things, R, XL and XC, because we know that Z is equal to, that is the impedance of the circuit will be given by R square plus XL minus XC square. So therefore, if we add all these R, XL and XC, Z will become like this. This is Z. So the minimum value of the Z is R, because, and the minimum value occurs when XL is equal to XC. So therefore this is omega C, or that is called the resonant frequency. Omega 0 you can say that is. So at resonant frequency, Z will be equals to R, and in that case XL and XC both will get cancelled each other. So therefore we can say certain conditions should be, which can be discussed for the series resonance circuit. That is, first point, minimum Z. That means the impedance will be minimum when the series resonance will occur, and that is equals to R. And if the Z will be minimum, then ultimately the current will be maximum. So you can say maximum current, and that is equal to V by R. Because we know that current is equal to V by Z. So if Z is equal to R, so I will be equals to V by R. Then if the net reactive component of the voltage becomes 0, so therefore the voltage and current will always be in the same phase in case of the resonance. So therefore, if voltage and current will be in the same phase, then the phase difference between the voltage and current will become 0. So therefore you can say, that is the third point, that we can say phi is equals to 0. And next point, if phi is equal to 0, power factor is equals to cos phi, and that is equals to 1. So these are the conditions under which we can say series resonance will occur. So now, whenever the Z becomes minimum, what happens to the current? So if you draw a graph Z versus I, the graph for Z. You know that current is inversely proportional to Z. Means current is equal to V by Z. So when the Z will be minimum, current will be maximum. And when Z is maximum, current will be minimum. So therefore we can draw a current like this. So this is the graph for current. So now see, when the Z increases, when the omega will increase, Z decreases up to certain value. This value is R actually. Then after further, by the increase of omega or frequency, Z also increases. Now again similarly, whenever the Z increases, the current will increase. So current increases to its maximum value. So we can say this is the maximum current I0 at resonance. So the current is maximum when Z is minimum, and that occurs only in the resonance condition, or whenever the frequency or angular frequency omega is equal to omega 0. So now we know that power is equal to I square R. So therefore we can say whenever the current is maximum at resonance condition, the power will be equals to I0 square R. This is the maximum power which will occur in the resonance condition. So now we are using a term half power. So half power means that is called half power, and that is equal to P max by 2. So P max by 2 means this will be equals to, you can say, I0 square R by 2. So this can be simplified by I0 by root 2 square into R. So that means the half power means the power becomes half when the current will be 1 by root 2 times that of the maximum current. So therefore what we say, this we can say 0.707 I0 square into R. So if we draw a line here, this is 0.707 I0. That means this is the 2 points. This is 1 point and this is another point. So these are the two frequencies at which the current becomes 0.70% of the maximum, 70.7% of the maximum current, and during that period the power is half of the maximum power. So therefore these two frequencies are known as the half power frequencies. So this is the lower half frequency omega 1 and this is the upper half frequency omega 2. And the difference between these two frequencies, that is given as delta omega, and delta omega is given as bandwidth. Bandwidth of the circuit. So here delta W we can say delta W is equals to omega 2 minus omega 1. That is the difference between the two half power frequencies. So this is the bandwidth. Now another factor is being given for, that is called the quality factor, which will describe the quality of this circuit. Quality of this resonance circuit means that we can say what is the difference between the frequencies during which the resonance may occur. So that is called the quality factor. So the quality Q factor, that is we are saying. So generally it is given as omega 0 n by R, or we can say that is 1 by omega 0 CR. To find out the omega 0 again, we can say we will take the conditions at which the resonance will occur. So normally we know that the series resonance will occur whenever the two reactances becomes equal. That means we can say XL is equal to XC, because this is the condition at which these two voltages becomes equal, and therefore these two voltages, vector sum of these two voltages becomes 0. So if XL is equal to XC, you can say this is omega L is equal to 1 by omega c. So here, as resonance occur, this is the resonance condition, so therefore we can say the frequency is omega 0 and omega 0 here. So this is omega 0 square is equal to 1 by LC, or omega 0 is equal to 1 by root over of LC. So this is the resonant frequency, and this is known as the dynamic impedance of the circuit. Okay, so after getting all this about the resonance circuit, resonance in series circuits, we can discuss about the resonance in parallel circuits also. But whenever we are discussing about the resonance in parallel circuit consists of resistance, inductance, and capacitance in parallel. So therefore, we can get variety number of parallel circuits. Means either the resistance will be parallel with the inductance, and that will be parallel with the capacitance, or RL parallel to C, or R parallel to LC, like this. So therefore, if we take a parallel circuit of RLC for resonance conditions, we can say this is a coil, because whenever we are taking any coil consists of a winding which must have some resistance. So therefore, this is the resistance and this is the inductance, and along with that, a capacitance is in parallel. So this we can say a parallel circuit RLC. So in this circuit will be supplied now a AC source having voltage V and frequency F. Then a current I will flow through this, and this current will get divided into two parts. So one will be here, that is the inductive current IL, here it is IC. So now, just like in case of the series circuit, in a series circuit generally the voltage get divided. So therefore we are saying that the condition for resonance to occur there, the net reactive voltage should be equals to 0. Similarly, here what will happen, in a parallel circuit normally the current gets divided. So therefore we can say here also, in case of the parallel circuits, the resonance will occur whenever the net reactive current becomes 0. So if we draw the vector diagram of this parallel circuit, so here to take the vector diagram, we have to take reference the voltage, because this is the parallel circuit, voltage is common to both the circuits. So therefore, this is the reference voltage. Now, IC, here the two currents are there, IC and IL. The vector sum of this IL and IC becomes I, the total current. So therefore, IC, that is the current flowing through the pure capacitance. So now we know that in case of pure capacitance, current always beats the voltage by 90 degrees. So therefore, we can say here, this is IC and this is leading by 90 degrees. Similarly, here it is IL and this is an RL circuit. This branch consists of a resistance as well as an inductance. So therefore, as this is an RL circuit, so this will the current will lag the voltage, but not exactly 90 degrees, but somewhat less than 90 degrees. So therefore, this is IL. So now these two currents, IL and IC, if we add all these two currents, that will give you the total current IL. Now, if we resolve into its mutual perpendicular components, into active and reactive parts, IC, it is completely reactive. It has no active component. But IL have both active and reactive components. So therefore, we can draw like this. This is the reactive component. Suppose this angle is phi, IL. So therefore, this will be IL cos phi. This is the active component of the RL circuit current, and the reactive component of that current is IL sin phi. So now, as the conditions for the resonance to occur, the net reactive current should be equal to 0. So net reactive current means here it is IC, here it is minus IL sin phi. So therefore, for resonance to occur, IC minus IL sin phi f should be equal to 0. So in this case we know that IC is equal to V by XC. V by XC minus IL is equal to V by ZL, because here IL means this circuit consists of R and L both. So therefore you can say this is ZL. And sin phi L. Sin phi L means this is, you know that cos phi is equal to R by Z. Similarly, sin phi is equal to XL by ZL. And this should be equal to 0. Now the V part will get cancelled, or we can say that is V by XC is equals to V XL by ZL square. Now this V will get cancelled, so therefore ZL square will be equals to XL XC. And whenever we are saying XL XC, that is equals to 1 by omega 0 L into, this is omega 0 L into 1 by omega 0 C. So here ZL will be equals to R square plus omega 0 square L square. So this omega 0 will get cancelled. So therefore that becomes L by C. So now you can say here R square plus omega 0 square L square is equal to L by C. So now here from this we can be able to find it out. Omega 0 square L square is equal to L by C minus R square. So omega 0 square is equals to 1 by L C minus R square by L square. Or we can say omega 0 is equal to root over of 1 by L C minus R square by L square. So this is the resonant frequency for the parallel circuit. Here in this case, if we can neglect this R, this will become 0. So then automatically that will be equals to 1 by root over of LC, which we can say here for R is very less than L, means R is negligible with respect to inductance, then omega 0 is equals to, you can say, root over of 1 by LC. That means this is equal to 1 by root over of LC. See now here, in case of the series resonance also we are getting the same resonant frequency. And in case of the parallel circuit also we are getting the resonant frequency which will be same as that of the series resonance. But the condition is that here the resistance should be omitted or resistance should be negligible with respect to inductance. Then also similarly we can be able to find it out the quality factor for the parallel circuits, and also the bandwidth of these resonance conditions and the half power frequency also.